first lesson in Unit 5 discusses rational functions and the graphs of those rational functions. Now we're going to concentrate on the different components of the graphs, and we're also going to use our technology, so make sure you have your graphing calculator handy. So first, let me get this out of the way. We're going to have a goal of graphing what we call simple rational functions, and those functions are going to be in this form right here. In this form, we're going to be able to tell where the vertical and horizontal asymptotes are very quickly, and these are going to be just our generic rational functions. And then later on, we're going to discuss more complex rational functions, which will be in this form. So first, a simple rational function is in this form right here. Now you might recognize some similarities between some other functions that we've learned about, and that has to do with the h and the k. Remember, h was the horizontal shift, and it always does opposite of what you think because this negative is part of the formula. K is going to be our vertical shift, and we'll see what that does to a rational function in just 1 second. So the first thing we need to do is grab our graphing calculator and type 1 over x into the y equals menu. And when you get your window set up, I just want a standard window at first. Well, actually, let's make our window match what's on our paper. So it looks like it goes from -6 to 6 for both the domain and the range. So let's change that to say -6 to 6, -6 to 6 for the y's as well, or the range. Alright, there we go. Now if you have an older calculator, it might, and you can't really tell here on this one, but it might be drawing a connection between what we call these two branches. That is a fault of the calculator and its capabilities as a graphing mechanism, so we'll talk about why that's not really there in a second, but this is what the graph looks like. Now they want you to fill out a t-chart, so let's go grab our table so we don't have to think too hard. And they want us to start at -4, so fill in your t-table. With decimals is fine. If you wanted to do fractions, that's fine too. And remember, whenever I graph, it doesn't turn out so hot. Whoops. So be careful when you graph. Two, 1, 1/2, 1/3, and 1/4. Okay, so you're going to graph this by plotting all those points, and I'm going to do a really sloppy job right now just because it's too hard for me to graph on the tablet, but you're going to connect them, and it's going to look, oh geez, that's really bad. Something like that. Oh, that's even worse. Okay, well the important part is that you realize that there are arrows on either end of these branches. This graph has some vocabulary associated with it. It is called a hyperbola. Not hyperbola, but hyperbola. There's what we call a horizontal asymptote on this graph. And remember, we saw these on the growth and decay functions. Right here, there's a horizontal asymptote when it's not shifted. Whoops, excuse my marker. The horizontal asymptote, of course, we see now is the x-axis. And then if you go back to the graph, if you ignore my red line, there's also a vertical asymptote along the y-axis. The domain and range are going to be every single number except, since there's an asymptote at the x and the y-axis, they're all numbers except 0. The graph has two symmetrical parts, and we're going to call those branches. And then for each xy pair, there's a corresponding -x, -y on the other branch. So if it goes through the point 1, 1, it's also going to go through the point -1, -1. Now that was a simple rational function that was centered, let's say, at the origin. But the shifts that we know that were true for parabolas and growth and decay functions and square root functions are also true for rational functions that are in this form. So remember, the h is going to be our horizontal shift. And you always have to think opposites when you think about horizontal shifting. And then the k is going to be our vertical shift. And then the asymptotes We're going to talk about that in a second. Let's go back up to our function here. Knowing what you know about horizontal shifting, if this represents the horizontal shift, we know since it's opposite, that means this guy has actually been shifted left 3 units. And then if the -1 represents the vertical shift, we know that that must mean this whole function was shifted down 1 unit. So what that means for our horizontal and vertical asymptotes is our horizontal asymptote used to be at 0. But if I was shifting it left 3 and down 1, the left 3 doesn't affect a horizontal line, but the down 1 sure would. So instead of having a horizontal asymptote at 0, now you're going to have a horizontal asymptote at -1. And then your vertical asymptote is also shifted left 3 and down 1. Well, the down 1 doesn't do anything to a vertical line, but the left 3 sure would. So your vertical asymptote is now at -3. So I would start by drawing in the two asymptotes, because when I graph this, I have to be as accurate as possible. Now you guys are not familiar with what these look like right now, so I'm going to expect you to grab your calculator, go to y equals, and type in the function. So in this case, it's 2 divided by the quantity of x plus 3, make sure that's in parentheses, and then subtract 1. And then plot some accurate points by going to your table and plotting whatever you can. And you're going to see there's some errors on this table. That's because of the asymptotes. There's one at -3, you see. Go ahead and plot whatever you can. And then when you hit graph, you're going to see that it kind of follows this. So I'm just going to kind of really terribly graph it. Again, I need your graphs to be superior to mine, as always. And they want to know, what does the A do to the graph? Well, it's the same A that we saw in all of the other graphs we've ever done. So if the A is greater than 0, then the rational function is going to look like this, like the one we just drew. And one might argue that it's going to be in certain quadrants, but that's not really true if it's been shifted. Now, if the A is less than 0, meaning it's a negative number, what that's going to do is it's going to flip your rational function so that this other branch on the left side actually is going to go up, and the right branch is going to go down. So it's going to be still a reflection over the x-axis like it always is. And the last question says, where are the asymptotes? Because this will be a good generalization for you as you do your homework. Well, we saw that this guy had a vertical asymptote at the opposite of this, right? So if we look at our formula, the vertical asymptote is going to be at the equation, I'm going to write down vertical asymptote, shorthand, at x equals h. Now remember, in this example, the h was really a -3, and that's why it's x equals h. And then your horizontal asymptote is going to be at wherever the k value was. So it's going to be at the line y equals k. So we talked here in this section about the translations and how they're the same sort of translations that we saw in a quadratic. So inside by the x moves it right and left, and then outside moves it up and down. And the important thing to remember is the x shifts always do opposite of what it looks like at first. So what I want you to start with here on number 1 is tell me how this was shifted. So the x minus 2, this part of the function, means a horizontal shift, and remember opposites, so this moved it right 2 units. And then this +1 off to the side means it was shifted up 1 unit. So the next thing I want you to do is graph your horizontal and vertical asymptotes. So remember, your vertical asymptote is x equals whatever your h value was. So in our case, it's going to be x equals 2. And your horizontal asymptote is going to be y equals your k value, so y equals 1. And I'm going to graph in both of these asymptotes with highlighter of some sort, so that way when I'm graphing, I don't accidentally cross it. And then at this point, because of your limited knowledge of rationals, what I expect you to do is go to your calculator and type it in and get some points and plot them. I'm going to cheat, and I'm not going to do a very good job of it. Oy. That was a terrible job. It should be hugging the asymptotes, but this is really difficult to graph on this kind of a function, on this kind of a device. Do a little better job here. Okay. Again, you're going to be plotting points to make this more accurate, but things I'm going to be looking for obviously your plotted points. I'm going to be looking for the asymptotes that are not crossed. And you see down here, it looks like I kind of started to cross the asymptote, so be careful. And just in general, I need your graphs to be really pretty, so that means graph paper when you're doing your homework. Let's talk about number 2. X plus 2 means things were shifted left 2 units. And then this plus 3 off to the side means everything was shifted up 3 units. Morning, Mr. Dredge. That was Mr. Dredge if you heard him. So if we talk about our vertical asymptotes, remember it's x equals the k value. So in our case, it's x equals -2. And then our horizontal asymptote is y equals 3. So let's go ahead and graph these in. And again, this is a section of our unit where if you don't have a graphing calculator, you're not going to be very happy because you're going to have to do a lot of things by hand, or come in and use mine. Now again, you're going to use your calculator to get table points, and you're going to plot them, and you're going to see that this rational function looks like this. Okay. Number 3. X minus 3 means it was shifted right 3 units. And then a -2 means it was shifted down 2 units. So for our vertical asymptote, it's now at x equals 3. And our horizontal asymptote is now at y equals -2. Whoops, I didn't graph that very well even. Draw in your asymptotes.
See, now, my door...
Well, that was Mr. Dredge again. All right, so you're going to use your table, and you're going to pull some points off of it. And then you're going to graph in your rational function. Ooh, that was ugly. Again, you're doing a much better job than I'm doing right now because you're going to grab your table points and make a beautiful graph. All right, the next example, x plus 1 means this was shifted left 1. And then this -1 here means it was shifted down 1. So talking about our vertical asymptotes, that is x equals -1. And our horizontal asymptote is y equals -1, because it's down. So plot your asymptotes with some sort of a highlighter. It's not part of the graph, we're just marking it so that we graph accurately. Oh geez. And then again, pull your table points. And you're going to see a graph that looks like this. So these are the most basic type of rational functions that I could possibly give you. Let's numbers 1 through the next few. They just want you to identify some components. Now, could you use your graphing calculator? Absolutely. But I would like it if you could try to not use it and go off your knowledge of the equation, because it's actually going to be easier and faster on you. So first, think about your horizontal asymptote and which one of these values affected your horizontal asymptote. Remember, the up and down shifts, the vertical shifts, affect your horizontal asymptote. So since this was shifted down 1 unit, that means your horizontal asymptote is now at y equals -1. The horizontal shift will affect your vertical asymptote because that's what moves a vertical line. So your vertical asymptote is x equals 4. Now notice I've written equations for your asymptotes each time. You have to write the full equation. If you just wrote the number 4 and not x equals 4, I can't count you correct. Now domain, we can do it one of 2 ways. First of all, domain would be all of the x values. And if you think about what this graph looks like, it exists on every single x value except for where there is a vertical asymptote because there's an imaginary invisible fence there. And the problem that we run into is where it's x equals 4 because that's where the asymptote is. So one way to write the domain is kind of interesting. You write -∞ to 4 and then union 4 to infinity. This implies that every number is okay except for 4 because it jumps over 4. Notice the parentheses on 4? Well, the more simple way to write the domain, and I would accept this for this chapter, is just to say x cannot equal 4. So I'm thinking most of you will opt for this method. Okay, same idea for the range, except range is affected by a vertical shift because it's the y's. So y cannot be a negative 1. So if you'd like to write this the fancy way, so negative infinity to negative 1, union negative 1 to infinity, implying that you jump over the negative 1. Or if you'd like to be a little, whoops, no, x, we're supposed to do y's. If you'd like to be a little lazy, which is not a problem here, you can just say y cannot be a negative 1. So since I'm thinking most of you are going to do it that method, that's how I'm going to continue on in the notes. Alright, your horizontal asymptote is going to be affected by the up 2 shift. So your horizontal asymptote is now a y equals 2. The vertical asymptote is affected by the left 3 shift, so that's x equals negative 3. And then domain is what x cannot be, so x cannot be a negative 3 because that's where the asymptote is. And your range, your y cannot be the 2. So once you know the horizontal and vertical asymptotes, it's a pretty easy question. And it's even easier if you can look at the graph, but again, I would like it if you can do this without the calculator. Now the negative 1 that was up in the numerator, all that's going to do is take your rational function and reflect it over the x-axis. It does not affect the location of the asymptotes at all. So number 3, let's see, our horizontal asymptote is affected by the up 4 shift, so that would be y equals 4. And some kids, as they fill in the horizontal asymptote, go ahead and fill in the range and say y cannot be 4. And the vertical asymptote is affected by the right 3 shift, so it's x equals 3. And of course, if x equals 3 is the asymptote, then x cannot equal 3. That is our domain. And here on number 4, the horizontal asymptote is affected by the down 5 shift, so that's y equals negative 5. So I'm just going to go ahead and fill in the range. Y cannot be negative 5. And then the left 6 means the vertical asymptote was shifted to negative 6, which means my x's cannot equal negative 6. All right. So that was the original lesson for 9.2. What I've done in this lesson is I've combined 9.2 and 9.3. Now if all you missed was the first day of this lesson, you can probably stop here. But if you want to go ahead and listen to the rest of the lesson, you go right ahead. The next part of the lesson is about 9.3, and it's talking about rational functions that are in a little bit of a different form, and they look like this, which means you've got a polynomial over another polynomial, so you no longer have the h and the k to look at. So a couple of ideas that we need to think about. First, the x-intercepts are the real zeros of p of x. Whoops. So basically what that means for us is to find the x-intercepts, we need to set the numerator, because that's the p of x, equal to 0 and solve. Okay, the vertical asymptotes are the real zeros of q of x. That's kind of similar to what we just did in the last lesson, but q of x is the denominator, so to find the vertical asymptote equation, you're going to set the denominator equal to 0 and solve. And then the horizontal asymptote is a little strange. It's basically done by comparing the degree of the numerator and the denominator. And to know what that means, you got to look down at the next thing. So when they say compare the degree, we're going to look at top heavy, bottom heavy, and equal weight ideas. If the function is bottom heavy, which means the degree in the denominator is larger than the degree in the numerator, then you have a horizontal asymptote at y equals 0. So if it's bottom heavy, your horizontal asymptote is y equals 0. We'll talk about why that is in a second. If it's top heavy, that means there's no horizontal asymptote, but make a big star here. That means there is what we call an oblique asymptote. I know you don't know what this means yet. We're going to talk about it in a second. And if it's equal weight, meaning the degree in the numerator is the same as the degree in the denominator, then the horizontal asymptote is the ratio of the lead coefficients. So let's see this in action. First, they want us to find the x-intercepts. And if I go back to my chart, it said find the x-intercepts by setting the numerator equal to 0 and solving. So if I was to take my numerator and set it equal to 0 and solve it, I would get x equals negative 1. So right away on my graph at negative 1, I'm going to draw in an x-intercept. Now my vertical asymptote, if I look back at my chart, said set the denominator equal to 0 and solve. So if I went ahead and set my denominator equal to 0, and you don't have to write this out once you get good at these, but these are your notes, so take as much as you need. you would solve. So you'd add the 4, divide by 2, so you get the equation x equals 2. So I'm going to draw on a vertical asymptote at x equals 2. Remember, vertical asymptotes are not part of the function necessarily. They're not drawn in reality. We just draw the asymptote with a highlighter so we don't cross it. Now the horizontal asymptote is where we decide whether this is top heavy, bottom heavy, or equal weight. So we have to look at the degree of the denominator and the degree of the numerator. So for that, the degree is the biggest exponent, and I'm looking right here. X over x. So it looks like they are both first degree linear polynomials, which means they are equal weight. And our chart back here, our bullet points, said if they are equal weight, then the horizontal asymptote is the ratio of the lead coefficients. Well, our coefficients are the numbers in front of the lead terms, so we got a 1 over a 2, so your horizontal asymptote is at y equals 1/2, or 1 over 2. Now, since it was not top heavy, this stands for oblique asymptote, there is no oblique asymptote. And we can fill in the domain and range pretty easily. The domain we see from our asymptote, x cannot be 2. And our range, because of our horizontal asymptote, y cannot be 1/2. Now we're not done, we still need to grab some points and plot, but you remember what I said about my graphs, they're never pretty. So do the best you can from your table to plot as many points as you need to graph this accurately. And you're going to get a rational function that looks like that. So the horizontal and vertical asymptotes were as obvious in this type of a setup, and we're going to see that not every rational function looks like this with 2 branches. Some rational functions look very, very strange. I want to discuss the horizontal asymptote idea briefly. The horizontal asymptote is really a question about end behavior. So what is your y value approaching if you were to put in really, really, really huge or really, really, really small numbers? So if I was to put in gigantic numbers for x, so like, let's say 1,000,000. So if I put in 1,000,000 right here and 1,000,000 right there, I would get y equals 1,000,000 plus 1. And then 2 times 1,000,000 would be 2,000,000 minus 4. Now I just randomly chose 1,000,000, but I could have gone bigger. I could have gone a billion, trillion, whatever. I don't even know what comes after that. Can we all agree that if you were to plug in huge numbers, this plus 1 and this minus 4 really become negligible? Like, I don't even have to consider them because they're so small in comparison to everything else. So all I really have to look at is what's happening right here. Well, 1,000,000 divided by 2,000,000 is really just a 1/2, and that's why our horizontal asymptote came out to y equals 1/2. We're going to see this same idea in a different type of function, and it's coming up in a couple examples. All right, the first problem says x-intercepts. For this, remember you take your numerator and set it equal to 0. Now, unfortunately, we have a quadratic, but you guys are really good at solving quadratics now. This is a factorable one. So it's x minus 3 and x plus 1. So if I solve that, I have an x-intercept at 3, and I have an x-intercept at -1. Let's go ahead and plot those. And then, let's see, the vertical asymptote is where you take your denominator and set it equal to 0. Well, be careful. If you set x squared minus 4 equal to 0, and you solved it, you would get both positive and -2 because of the plus or minus. So we have a vertical asymptote at -2. Ooh, I'm not graphing so hot today. And then at +2. Okay, horizontal asymptote. I have to look at my degree of the top and the degree of the bottom. So let's look at the lead coefficients. It's a squared over a squared. So again, we have an equal weight fraction, which means that you just look at the lead coefficients. That's a squared right there. So we got a 1 over a 1, which means my horizontal asymptote is a 1. And the same idea applies as the last example. If you were to put in 1,000,000 and then square it, you would end up with huge numbers right here, and these guys would actually become negligible in comparison to it. So that's why we only look at the lead coefficients. And then since it's not top heavy, there is no oblique asymptote. The domain is that x cannot equal positive and negative 2. And the range is that y cannot equal a 1. Ew. I never drew in my horizontal asymptote. Oh goodness. Definitely not drawing so hot. Okay, so I even don't know what this guy looks like for sure. I think I have an inkling, but you guys don't have a lot of experience with these, so I would expect you to do is go to y equals and type in your function. So make sure you use parentheses. We've got x squared minus 2x minus 3 divided, and then use parentheses for the denominator, x squared minus 4. And of course you're going to use your table to get some good points, but I'm just going to go ahead and kind of cheat using this. Ooh, that's lovely. So, looks like this guy has a branch up here. Oh, that's not good, sorry. This is a unique case where I know it kind of seems wrong that it's going to cross this horizontal asymptote. It's not that you can't cross a horizontal, asymptote. It's just that on the ends, you can't cross them once you go off on your far ends of the graph. So you can cross it, you just can't continually cross it. And then this bottom branch kind of came up like, oh geez, this. Do a much better job than I just did. But that is approximately what this rational function looks like. Very atypical of what we were just working with our simple rational functions. So they're not all going to look beautiful. Okay, the x-intercept for number 3. Normally I take my numerator and try to set it equal to 0, but if you notice, there is no x value in that numerator. So 4 can never equal a 0, therefore there is no x-intercept in this problem. Now for your vertical asymptote, I would try to set my denominator equal to 0 and solve, but as you see here, we're going to end up square rooting a -1, which gives us i's. We can't graph i's in this chapter, so there's actually no vertical asymptote either. Okay, look at your degree. This is a degree of 0 because there's no x's over a degree of 2, so this is more x's in the bottom. It's heavier in the bottom, so we call this bottom heavy. And if you go back to your little bullet points, it said that when you have a bottom heavy equation for rational function, that meant that your horizontal asymptote was at y equals 0. We'll talk about that in 1 second. And since it's not top heavy, there's none for the oblique asymptote. This is kind of a boring function. The domain is, there's no restriction for a vertical asymptote, so it's everything, so -infinity to infinity. And the only thing that would affect the range would be if y was equal to 0 because of the asymptote, so y can't be 0. All right, if you go to your calculator and you graph this, I think it's got a intercept of 4, it's going to look like this, and I'm going to do a really bad job, but hang with me. Oh, excuse me. Okay, so very atypical from what we have just seen. Let's talk a little bit about why the horizontal asymptote is at y equals 0. It's the same idea. If you were to take your function and then plug in 1,000,000 in for the x, you would get 4 divided by, now 1,000,000 squared, let's see, 6 zeros squared, okay, 12 zeros. Oh my goodness, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, plus 1. I think we can all agree that this 4 is really nothing in comparison to what's on the denominator. So what happens if you take a teeny tiny number and divide it by a gigantic number? Well, that number gets really, really, really close to 0. If you tried typing that on your calculator, you'd get something like, with e's in it, scientific notation, 2.7 e -17. I don't know, I'm just making that up. But that's why it always approaches 0. So if you forget your rules about top heavy, bottom heavy, and equal weight, think about plugging in 1,000,000 and what would that mean for your function? What would it approach for the y value? Okay. X-intercepts on the next one. If I tried to set this equal to 0, you would find out pretty quickly that you'd be square rooting something that's negative. which we know we can't do in this chapter, so there are no x-intercepts. If I took my denominator for the vertical asymptote and set it equal to 0, we do have a quadratic, but the good news is you've got a nice quadratic. You can take out the x, and you're left with 2x minus 3. And then if you set both of these equal to 0, you have a vertical asymptote at 0, and you have another one at, let's see, 3/2, which, if you want to write it as 1.5, that's fine. It might be easier to graph it if you know it's a decimal. Okay, horizontal asymptote. We have to decide if it's top heavy, bottom heavy, or equal weight. So I look at the degree. This is a quadratic over a quadratic. So it's equal weight, which means I'm supposed to just look at the coefficients now. So 5 over 2. So you can either write y equals 5 over 2, but again, sometimes it's easier to graph the decimal. 5 over 2 is the decimal 2.5. And then there's no oblique asymptote because it's not top heavy. And domain, x cannot be 0 and x cannot be 1.5. And for range, y cannot be, and you can either say 5/2 or 2.5. All right, graphing in the asymptotes now. All right, it's a little hard to graph on the axis, so if you have a highlighter, it might work better. Oh, goodness. How gross. Okay. So, if you graph this on your calculator, it's not going to give you a real great idea of what this looks like, because it's kind of strange. Just make sure you use parentheses. 5x squared plus 8, close, divided by 2x squared minus 3x. Okay. If you would prefer a standard window here, because we do show a standard window on our paper, you might want to hit zoom 6. Oy. Oh, I'm glad I hit zoom 6. Do you see down here there's a little tiny bump? If I kind of extended my window down a little further, maybe I want my y-min to go to -20, you're going to see that there's essentially like a teeny tiny parabola looking thing down there. So, it's kind of off the chart here, but something like this. And then, oh geez, you make sure you plot points, because this is ugly. And you look something like that. Let me just double check on my calculator. Yep. Oh, what actually happened, and I didn't do a real good job of this because I never pulled up table points, but this branch here actually I think came down underneath the asymptote and then crossed again. It crossed once and then came back up on the bottom side. So I think it did something like this. Oops. And then kind of hugged this asymptote in the end behavior. So I just did a really terrible job of graphing that. Hopefully yours will be better. Our next example, oh good, interesting one. Normally, to find the x-intercepts, you set your numerator equal to 0 and solve, and this one's factorable. I think we've actually seen this problem before today. So your two x-intercepts are going to be at, and you don't have to write x equals for this because we assume they're x equals if they're x-intercepts. So at 3 and -1. Now your vertical asymptote would be if I set my denominator equal to 0 and solved, so that would be x equals -4. I'm going to go ahead and fill in my domain while I'm here. Okay, your horizontal asymptote. This is an interesting one. Notice that there's a quadratic over a linear, so there's a higher degree in the numerator, which means this guy is top heavy. And since it's top heavy, that means there's no horizontal asymptote, but that does mean we have what's called an oblique asymptote. Oblique asymptotes are diagonal asymptotes, generally linear, but in order to find it, and this is the fun part, you get to do long division. Now the good news is, it's not that bad because you don't have to finish the problem. You're going to take your numerator and divide it by the denominator, which is essentially what this problem is asking you to do. So remember we just start with the first leading terms when we do long division. So x squared divided by x would be x. And then you multiply x squared plus 4x. And then the next step in long division is to subtract. So -2 minus 4 would be, careful, a -6x minus 3. And here's why I kind of like this. Once you do this last division, you're done. So -6x divided by x would be a -6. We are done. The result of your long division problem, this guy, don't worry about remainders at all. This is the equation of your oblique asymptote. So I'm going to write down my oblique asymptote is the line y equals x minus 6. Now you have to remember, when you graph an asymptote, you have to actually graph the line. So if I was to graph that line, I would start at -6, and he would have a slope of 1, so it'd kind of continue forever. Eventually it would cross over here. So do the best you can. Kind of draw, oh geez, that's terrible. Alright. And then, definitely you want to go to your calculator and type this guy in. I didn't draw in my vertical asymptote yet. -4. Okay. I guess I should have extended this a little longer. Probably if I had my life to live over again, I would have given you a different set of graph paper to graph this in, but it looks something, oh geez, like this. Okay, so again, get your table points, plot what you can. I know it's going to fall off of this graph pretty easily, but this is what he looks like. All right, number 6, we have another example of a top-heavy fraction. So we're going to have to do the same sort of thing where you do long division to find the oblique asymptote. So the x-intercepts would be, if I set this numerator equal to 0 and solved, so I'd try to factor it, of course. Whoops, that's a 1. So let's see, we have an x-intercept at -7 and at 1. A vertical asymptote would be setting your denominator equal to 0, so the equation x equals 1 is my vertical asymptote. Oh, uh-oh, something happened. Back up, Abruzzo. Alright, erase everything we just did. What you're really supposed to think about, and we ran into this pretty quickly, is when you factor your rational function, sometimes something algebraically reduces. So for instance, look right here. This is really equivalent to my problem. Do you see that the factors of x minus 1 and x minus 1 are going to end up canceling out? This is what we call a removable discontinuity. And his unofficial name is quite simply a hole. So what happens is, at that value, which originally we thought there was a vertical asymptote or an x-intercept, neither one of those things exist, and we actually have a hole. So if you want to figure out exactly where the hole is, well, you know that it's at when x equals a 1, but you also need the y value. So when there's a hole at x equals 1, what you do is you go back up to your simplified equation once you cross off the parts that make a hole and plug in that 1. So 1 plus 7 would give us an 8. So x equals 1 and y equals 8. There's a gigantic hole. It's not really gigantic at all. So your calculator won't really show you this. So what you're going to have to do is just graph that in. Now there still is an x-intercept at -7. But now that we've removed that discontinuity, you're not going to see a vertical asymptote, you're not going to see a horizontal asymptote. At first glance we thought there was an oblique asymptote, but because these things removed because of the hole, there's actually none. There was an x-intercept, I said, at -7. There is just one issue for a domain, and that is the x value of the hole. So we see now that x cannot equal 1, and then the y value of the hole is going to be your range issue. Y cannot equal the 8. And kind of interesting, since we remove the x minus 1s, all we're left with is the function y equals x plus 7. And that's essentially what we're going to graph, with this small exception, oh geez, pretend that's a line, of where this hole is located. So what I need you to do, even though your calculator is not going to show you this really obviously, is where the hole is, put a really exaggerated open circle, showing your teacher that you realize there is nothing at that point. It's a discontinuity, and that is a rational function, which actually turns out to be not a rational function at all anymore. Okay, number 7. If I tried to set my numerator equal to 0, I'd get i's, so there is no x-intercept. If I set my denominator equal to 0, I would probably take out a 3x first and get x minus 2. And if I set both of those equal to 0, I get x equals 0 and x equals 2. For my horizontal asymptote, I see that these are quadratics over quadratics, so these are equal weight, so I'm supposed to look at the coefficients, 1, 3, so y equals 1 over 3, which means there's no oblique asymptote. Domain means x cannot equal 0 or 2. And range, y cannot equal 1/3. So you're going to graph in both of those parts,